Okay, so in this video, we're going to be looking at forces on planar submerged objects, and we're specifically looking at the net force on a submerged gate. So in this problem, we have a gate that is distance d down from the free surface and hinged at A, and this gate is at an angle theta with the seafloor. And our normal assumptions when we're looking at the hydrostatic pressure equation are we're dealing with a static fluid, we're neglecting surface tension, we're looking at an isothermal and incompressible system, we're looking at a constant gravitational field, and we have a uniform and constant ambient pressure. So we have P infinity above the free surface, and we have P infinity behind the gate. So we have P infinity all around this problem right here, and hydrostatic pressure from the liquid is acting on the gate on this upstream side. So we're given that the density of the water is about 1,000 kilograms per meter cubed, D is equal to 3 meters, L is equal to 5 meters, L is the length of the gate, W is equal to 6 meters, W is the width of the gate, and theta is 40 degrees. The objective here is to find the net force on the gate, so let's start with that. So here on the left-hand side, we're just redrawing the problem with our distance h, where h is the h in P equals P infinity plus rho gh, which is just the hydrostatic pressure equation. So if we look at an arbitrary point on this gate, this point P right here, and then we kind of blow the gate out in x and y such that we can kind of see the two-dimensional view of the gate, we see that this point P right here is actually a distributed pressure, a line pressure across the width of the gate. And if we look at the differential element of that gate of height dx and of width w, you can see that P is distributed uniformly along that differential area, right? And what we're going to try and do is take the pressure on that differential area and integrate it over the entire length of the plate. So in this next slide, that's exactly what we're doing. We're integrating the net force on the gate over the length of the gate. And you can kind of imagine, if you go back to the previous slide, that on the other side of this gate, you have P infinity. So on the side of the gate with the water, we'll call it, you have P, and on the side of the gate without the water, we have P infinity. So the net pressure on this differential area is P minus P infinity. Now, if you take that net pressure, P minus P infinity, and you multiply it by the differential area, which is just dx times w, then you have the net differential force on that differential element. And that's exactly what we have in this integral here. We're taking the net pressure, multiplying it by the differential area, and integrating it over the entire area of the plate. That will give us the net force on the plate. And what you end up getting is when you plug in for P infinity plus rho gh, you subtract P infinity, you get rho gh, w dx, integrated over 0 to L. When you pull out rho, g, and w, as you see here, you're left with an integral from 0 to L of h dx. And unfortunately, we currently don't know what h is in terms of x, which you need to know if you're going to integrate h with respect to x. So the next problem is to find some mapping of h to x, or h as a function of x. So to express little h as a function of x, you can kind of realize that, again, little h is just the distance from the free surface to any given point in the gate. And therefore, we can express little h as a sum of two subdistances. This distance right here, which is d, which was given in the problem, it's just the height of that wall, and this distance right here, which is just the leg of this triangle. If we do some geometry, we could show that the theta that was originally defined, which is the angle between the gate and the seafloor, is the theta, or is the angle of the triangle right here. So doing some geometry, we could show that this theta is this theta, which is this theta, right? So now that we know that the angle of this triangle right here is theta, we could say that, well, sine of theta is equal to this distance right here over our coordinate x, which is the x coordinate along the gate at any given point we're considering. So if we call this distance big H, then we could say sine of theta is equal to big H over x. Then we could say that big H is equal to x times sine theta, and since we know that little h is equal to d plus big H, we could say that little h is equal to d plus x times sine theta. And again, this x right here is the x coordinate of the gate along its length at any given point. So if you look at the previous slide, you can see that this is how the x coordinate is defined. So at any given little h, that little h has an x coordinate associated with it. That is the x that we're examining in that expression. So now that we have h as a function of x, we can go back to where we were in the integral, which is right here, and complete the integration by plugging in the expression for h. So that's shown right here. We have the same exact expression as we left off with, except now we can plug in h as a function of x, and we can complete this integral. I won't go over the details of that integral, but we can complete this integral, and we see that the net force is equal to rho g wl times the quantity d plus l sine theta over 2. So if you then plug in the knowns that were given in the beginning of the problem, you can see that the net force is then equal to 1354.5 kilonewtons, and that is technically a magnitude, but we know it's in the direction from the water to the air because the pressure of the water is greater than the pressure of the air. The hydrostatic pressure from the water is greater than the hydrostatic pressure from the air. So the next question is, where does the net force act in XY? Where does the net force act on the plate? So in this view, we're looking at the pressure distribution on the gate versus the equivalent net force on the gate. So if you look at the gate along its length, so this is the hinge and this is the gate itself, you see that the pressure here is really the pressure here, the pressure here is really the pressure here, and the pressure here is really the pressure here. So that's how it kind of looks from an XY view to a side view. Now, what we want to do is take this pressure distribution, as we've shown here, and map that to the equivalent net force, which we've already done. We've calculated what the magnitude of that net force is. But now the question is, where can we apply this net force in XY to create an equivalent moment? So we've created an equivalent force. Where can we apply that equivalent force to create an equivalent moment? How do we find x prime and y prime? Well, we begin that on the next slide here. So what this primary expression right here is really saying is, if we go back to the previous slide, we could see that this pressure distribution, as shown right here, is creating a moment about this y-axis, right? So this pressure distribution down here is creating a net moment about this y-axis. This is what this integral calculates, that moment about the y-axis created by the net pressure distribution. So this P minus P infinity times dA, that's just a net differential force at the location dA. Now, if we multiply that by x, we get the net moment about the y-axis at that location dA. Now, if we sum that over the entire area of the plate, we get the net moment about the y-axis created by the net pressure distribution. So this is the net moment about the y-axis created by the net pressure distribution. So then this is saying, what x-coordinate do I need to multiply my net force by to get that equivalent moment about the y-axis? These are just equating moments. So performing out this integral is just a lot of the same stuff that we've done in the past. And we'll see that at the end of the day, what we get is this expression right here on the left-hand side, x prime times fn, which we've already calculated, which is this expression right here, is equal to this result of the integral right here. And doing a little bit more algebra, which again, I'll just leave on the screen here to follow along as you wish, we see that x prime, doing the algebra out, ends up becoming this expression right here, which is L times the quantity 3D plus 2L sine theta over 6D plus 3L sine theta. But then you plug in the knowns from the beginning of the problem, and you see that the result is 2.79 meters. So what exactly does that mean? This x prime is 2.79 meters. If you apply Fn 2.79 meters down this plate, it creates an equivalent moment about the y-axis as the net pressure distribution does. So we are almost there to an equivalent system, because again, we'd much rather deal with a single net force at a single location than the entirety of these line pressures applied over the entire area of the plate. This right-hand side is much easier to manage than this left-hand side. So again, if we go 2.79 meters down the plate and we apply Fn at 2.79 meters down the plate, then that Fn creates an equivalent moment about this y-axis as this net pressure distribution does. The same process applies for the y location of the net force. So this primary expression right here is essentially the same primary expression as we just looked at, except now we're looking at moments about the x-axis instead of the y-axis. So essentially we're saying, what y-coordinate do I need to multiply my net force by to create an equivalent moment as the pressure distribution does about the x-axis? So now you can perform integration on this primary expression just as we had previously done with the x location, except now with this particular integration, we end up with two special quantities that we should talk about. The first special quantity is the integral over a of y dA. That is the first moment of area A about the x-axis, and that is equal to the y-coordinate of the centroid of the area multiplied by the area. So you could just take this YCA and plug it in right here. The second special quantity is the integral over a of xy dA. This is not as famous of a quantity, but it is also important in statics and dynamics, and it is the first product of inertia of the area A about the x and y axes. Now what you can actually do with this second special integral is express it as the product of inertia about its x and y centroidal axes plus its area times its x-coordinate of its centroid times its y-coordinate of its centroid, which is this expression right here. You can use the parallel axis theorem to do that. However, I find it easier to just simply perform the integration on the particular shape, because this integral is usually not very hard, especially for symmetrical objects. So we're just going to perform this integration, but keep in mind, if the integration is too complex because the shape is too complex, you can use the parallel axis theorem to express this second integral as a summation of simpler terms. So actually performing that integral, the integral over a of x, y, dA, it's just a two-dimensional integral, as you can see here, because again, we just have a plate, we have our y-axis, and we have our x-axis, and we're simply just going to integrate x, y, dA. So there's a differential area associated with each section of this plate, and then you're just integrating the x and y coordinates of each differential area multiplied by the differential area over the entire area of the plate. So if you perform that integration, you end up getting the quantity LW squared over 4. So taking the expression from the previous page, rho GD, so we have the rho GD right here, we have the integral over A of y dA, well, that's just the first moment of area of the area, and that's equal to yCA, the y coordinate of the centroid multiplied by the area. We have our summation, we have our rho G sine theta, and then we have our integral over A of xy dA. That's just the product of inertia we just calculated for the plate up here, and we know that that is equal to LW squared over 4. Now we have an expression in terms of all variables that we know, and we can use algebra to simplify it. Then, using algebra to simplify it, we see that y prime fn is equal to this expression right here. Well, we know what fn is equal to in terms of variables. We had already solved for that. So, going to the next slide, we can then plug in fn in terms of variables and simplify and solve for y prime. Simplifying for y prime, it turns out that when you plug in fn here, and you plug in the expression that we just calculated in the previous slide here, and you simplify for y prime, you see that it's just equal to w over 2. And that makes perfect sense, right? So if you go back to the previous slide, or a couple of previous slides, so looking at the gate in this view right here, we can remember that pressure increases with depth, and depth increases with x, and so pressure increases with x. So if we look at this side view, actually, we can see that x is in this direction, so depth increases with x, and so pressure increases with x. So as we go down in x, the pressure is increasing. Along y, along the width of the plate, depth is not changing at all, and so pressure is not changing at all. So pressure is only changing as we go down in x. It's not changing at all as we go across in y. So if you view this as the net force should be applied at the center of the distribution, then you can imagine that the center of the distribution in x is below the half length of the plate because more of the distribution is in the lower half of the plate than the upper half of the plate. Now, the center of the distribution in y is right in the middle of the plate, or the half width of the plate, because the distribution is not changing in y at all, right? So that's another way you can think of it, and it kind of makes it a little bit more intuitive. So back to where we were, we could see that w over 2, which is just y prime, is equal to 3 meters with the variables, with the values that we were given in the beginning of the problem. So y prime is equal to 3 meters in this case. Now, how do we translate this to something that we can actually look at and understand? So again, we've solved for the net force, it's 1354.5 kilonewtons. We've solved for x prime, it's 2.79 meters. We've solved for y prime, it's 3 meters. So the original problem really looks like this. We have a gate, and we have a pressure distribution on that gate that increases linearly with depth, and we have a net pressure distribution on that gate because we have hydrostatic pressure from water on one side and hydrostatic pressure, or uniform pressure really, from air on the other side. Now, how do we translate this net pressure distribution to a single net force acting at a singular location? Well, that's what we just saw for up here. So what we can say is, instead of looking at this pressure distribution in 2D, we can look at the singular net force that we saw for at the singular point that we saw for. So keeping our view in xy as we have here, we could say this pressure distribution is equivalent in both force and moments to this system right here, or a net force of 1354.5 kilonewtons applied at 2.79 meters along x and 3 meters along y. So applying a singular net force at this point right here is equivalent in both force and moment, net force and net moment, to this pressure distribution right here. And then looking at the side view, we can see that 1354.5 kilonewtons is applied at 2.79 meters down from the hinge, or right below the half length of the plate, and that's because, again, more distribution is on the lower half of the plate than the upper half of the plate. So we're just below the half length of the plate here for our equivalent location. And one important thing to note is that the net force is applied perpendicularly to the plate, just like the pressure acts perpendicularly to the plate, right? So this net force acts at a right angle to the plate because the pressure, the net pressure, also acts at a right angle to the plate. So in summary, instead of having to look at this more complex two-dimensional pressure distribution, we can translate this more complex two-dimensional pressure distribution to a singular net force acting at a singular point. And this singular net force acting at this singular point creates an equivalent force to the pressure distribution and equivalent moments about the x and y axes as the pressure distribution. So this system right here is equivalent to this system right here. So that should be it for this video. I really appreciate you watching. Thank you very, very much. And I will see you next time.